Hello there, and welcome to the Sleepy Nature channel. Tonight, we are going to drift together into one of the quietest and most beautiful secrets the natural world holds: symmetry. Did you know that a single snowflake falling through cold winter air carries within it a perfection so precise that no two have ever been exactly alike? And yet, every one of them is perfectly balanced, 6 sides, always 6, each one a mirror of the others. Or that a sunflower arranges its seeds in 2 sets of spirals, one curling left, one curling right. And the numbers of those spirals are always from the same ancient mathematical sequence that appears in pine cones and galaxies and the curl of a Nautilus shell. The world around us is quietly, gently arranging itself into patterns of the most tender balance, over and over, in every leaf and every wave and every wing. Take a slow breath now. Let your shoulders settle. You don't need to be anywhere tonight except right here, listening. Let the world outside grow soft and distant. Let the air around you feel warm and still. We are going to walk gently through the symmetry of nature together. And somewhere along the way, without even noticing, you are going to fall asleep. There is a kind of quiet geometry in the world that you don't have to look very hard to find. It lives in the things you already love, in the shape of a leaf, in the face of a flower, in the way a butterfly holds its wings open in the sun. It is symmetry, and it is everywhere. Let's begin somewhere soft and simple. Think of a maple leaf. You have probably held one before, maybe as a child, maybe just last autumn, pressing it between your palms to feel its papery warmth. If you folded that leaf right down its center vein, one half would lie almost perfectly on top of the other. The lobes would match. The curves would echo each other. This kind of symmetry, the kind where one side mirrors the other, is called bilateral symmetry, and it is perhaps the most common kind of beauty in the natural world. The reason leaves tend to grow this way is something gentle and practical. A symmetrical leaf catches light more evenly. It distributes the work of photosynthesis in a balanced way across its whole surface. Nature, when left to its own quiet patience, tends to find the most efficient form. And the most efficient form is very often also the most beautiful one. Now think about a fern, not just one frond, but the whole plant. A fern frond has a central spine, and from that spine grow smaller leaflets, each one a miniature version of the whole frond. And each of those leaflets has its own smaller leaflets, each one a smaller echo still. This is a different kind of symmetry, not just left mirroring right, but a pattern that repeats at every scale. Mathematicians call this self-similarity. We might just call it the feeling you get when you look closely at something and realize it contains itself. The bracken fern, which grows in great soft drifts across hillsides and forest floors, does this so precisely that a single leaflet removed from its frond looks almost indistinguishable from the whole frond when held at the right distance. Nature makes no wasted gesture here. Every part is shaped by the same quiet instruction. Let your breathing slow just a little more. There is no hurry. We have all night. A spider builds its web in the dark, guided by nothing but instinct and the tension of silk between its legs. And yet, the finished web is a radial masterpiece, threads extending outward from the center like the spokes of a wheel, connected by spiral threads that catch the dew in the morning. The orb weaver spider, the most familiar kind, produces a web that has a kind of rotational symmetry. You could rotate it around its center by a certain angle, and it would look the same. This is the same symmetry found in starfish, in sea urchins, in the blooms of certain flowers. There is something deeply restful about radial symmetry. Perhaps it is because it suggests completeness. Every direction accounted for, no edge left without its mirror. When you look at the center of a sunflower, you're looking at thousands of tiny flowers arranged in a spiral that radiates outward with perfect balance. It is hard to look at a sunflower and feel anything but peace. The sunflower's spirals follow the Fibonacci sequence, a series of numbers where each one is the sum of the two before it. 1, 1, 2, 3, 5, 8, 13, 21, and on and on. If you count the spirals curving one way in a sunflower head, and then count the ones curving the other way, you will almost always find two consecutive numbers from this sequence. 21 spirals in one direction, 34 in the other, 34 and 55. This is not coincidence. It is the deepest kind of natural economy, the most efficient way to pack seeds into a circular space. And this same sequence appears in pine cones, in the arrangement of leaves around a stem, in the scales of a pineapple. Nature returns to it again and again because it works, because it is balanced, because something in the physics of growth leads living things back to this quiet mathematical harmony. Let yourself settle a little deeper into wherever you're lying or sitting. Let the weight of the day begin to lift. Outside somewhere, a pine cone sits in the dark on the forest floor, its scales spiraling in Fibonacci patience, waiting for spring. The wings of a butterfly are perhaps the most immediately recognizable symmetry in the natural world. Hold one gently in your mind right now, a monarch butterfly perhaps, with its deep orange and black. The left wing and the right wing are almost perfect mirrors of each other. Every spot, every vein, every curve of orange repeated on the other side. This bilateral symmetry is so precise in butterflies that scientists use slight asymmetries, tiny departures from perfect balance, as a measure of environmental stress. A perfectly symmetrical butterfly is a healthy butterfly. Beauty, in this case, is genuinely a signal of well-being. The patterns on butterfly wings are made by thousands of tiny scales, each one a single cell's width, overlapping like the tiles on a roof. The color comes not always from pigment, but from the microscopic structure of the scales, which bends light in specific ways. A morpho butterfly's iridescent blue, that electric shimmer, is not blue at all in the way a painted wall is blue. It is structural color, light playing against a lattice too small to see. And this lattice is arranged with perfect symmetry across both wings. If you have ever felt the strange calm of looking at a butterfly, it may be partly because your brain recognizes the symmetry and reads it as safety, health, wholeness. We are wired, somewhere deep down, to find symmetrical faces and forms beautiful. It is an ancient recognition. The natural world has been speaking this language long before we had words for it. The face of a flower speaks it too. Take a daisy, that most cheerful and uncomplicated of flowers. Its white petals radiate outward from a golden center, each one roughly the same length, the same width, arranged with an evenness that is almost mathematical. The center disc, if you look closely, is made of hundreds of tiny individual flowers packed in those Fibonacci spirals again, a golden circle of perfect order surrounded by the simpler radial pattern of the petals. Botanists classify flower symmetry carefully. Flowers with radial symmetry, like daisies, sunflowers, roses, can be divided into equal halves along multiple axes. Flowers with bilateral symmetry, like orchids, snapdragons, violets, have only one line of symmetry, one way to fold and find a match. Both kinds are beautiful. Both are deeply purposeful. The shape of a flower is a conversation with its pollinators, a landing platform, and a signal all in one, shaped by millions of years of quiet negotiation between plants and the creatures that visit them. And somewhere in a warm garden, a bee is landing on a flower right now, matching her body to the bilateral symmetry of a violet, because her tongue is exactly the right length for this particular flower's depth. They have grown toward each other over time, these two living things, shaped by the same patient forces. There is something very peaceful in that thought. If you feel yourself growing heavy and warm, that is exactly right. If you would like to leave a comment below about your favorite flower, the one you picture when your mind needs somewhere gentle to go, please do. It's always such a lovely thing to read, and if this is helping you find your way to sleep, a like on the video helps more people find their way here too. Now, let's keep going. We are only just beginning. Crystals grow in the dark and the cold and the pressure of the earth, and they grow with a symmetry so precise it seems almost impossible. A grain of salt, ordinary table salt, is made of sodium and chloride ions arranged in a cubic lattice, and if you could see it under a powerful microscope, you would find perfect right angles, perfect repeating cubes stacked in every direction. This is why when you spill salt and look at it in good light, you might catch tiny cubes glinting among the grains. Snowflakes are water crystals, and they are the most famous example of natural symmetry in the cold world. Each snowflake begins as a single ice crystal around a tiny particle of dust high in the clouds. As it falls, it encounters different temperatures and humidities, and it grows. But it grows in 6 directions simultaneously, and because all 6 arms experience the same conditions at the same time, they all grow in the same way. The result is 6-fold symmetry, 6 arms, each one the mirror of the others, each one a record of the snowflake's journey through the air. No 2 snowflakes are exactly alike, because no 2 travel exactly the same path through exactly the same conditions. And yet, all of them are 6-fold. All of them carry the same quiet geometry. There is something in that. The idea that infinite variety can live inside a fixed and balanced form that feels like a kind of freedom. Let the thought of snow fall gently over you now, soft, cold only in the way that clean air is cold, refreshing, not harsh. The world outside is settling. You are settling too. A river from above traces patterns into the land that are as symmetrical as anything drawn by hand. A river bends and curves, and those curves are not random. They follow a mathematical relationship so consistent that engineers and geographers have given it a name, the meander ratio. The width of a river and the radius of its bends are related in a way that holds across rivers of every size, from a tiny stream in a mountain meadow to the great slow curves of the Amazon. If you could fly high enough to see a river plainly, the way a bird sees it, you would notice that the landscape around it seems to lean in toward the water, that the bends form a kind of sinusoidal wave moving across the flat land, each curve answering the last one. Left, then right, right, then left. A kind of bilateral rhythm laid across the earth by nothing more than water and time. Breathe in slowly, breathe out. The river doesn't hurry, it never has. The inside of a Nautilus shell is one of the most quietly famous images of mathematical beauty in nature. The shell is divided into chambers by curved walls, and the animal lives in the outermost one, moving into a larger chamber as it grows, sealing the old one behind it. The shell grows in a spiral, and it is a very specific kind of spiral, a logarithmic spiral in which each new turn is a fixed proportion larger than the last. If you draw a line from the center of the shell outward and measure the distance to the shell wall at regular intervals, you find the same ratio repeated again and again and again. This ratio, often called the golden ratio, or phi, appears so often in natural growth patterns that it has become almost mythological in the popular imagination. It appears in the spiral of a hurricane as seen from space, in the curl of a breaking wave, in the shape of a galaxy. Whether it appears quite as universally as it is sometimes claimed is a question for careful scientists. But it is certainly there in the Nautilus. And in the Nautilus, it is genuinely beautiful. The shell of a Nautilus is also bilaterally symmetrical when seen from the outside. The left half mirrors the right. The top curves answer the bottom. It is a shape that seems to have thought deeply about itself before arriving at its final form. Let your thoughts grow quieter now. Let them become like water in a still glass, present but not moving. The symmetry in a honeycomb is one of the great engineering wonders of the natural world, made by creatures with brains no larger than a sesame seed. Bees construct their honeycombs from wax they produce themselves, and the cells they build are hexagons, six-sided shapes that tile together without gaps, without overlap, using the minimum possible amount of wax to enclose the maximum possible amount of space. Mathematicians proved in 1999, though bees have known it for millions of years, that the hexagonal tiling is the most efficient way to divide a flat surface into equal cells. No other shape manages it better. Squares waste space at their corners. Triangles require more material. Only the hexagon achieves perfect efficiency. And the bees have been building hexagons for at least 100 million years. The honeycomb has a six-fold rotational symmetry, rotated by 60 degrees, and it looks exactly the same. It also has multiple lines of reflective symmetry. It is, in a sense, a crystalline structure made by living creatures, driven by the same forces of efficiency and physics that make crystals grow the way they do. Inside a hive, the temperature is kept at exactly 35 degrees Celsius, the perfect temperature for developing larvae. The bees manage this by clustering together and vibrating their muscles to generate heat when it is cold, and fanning air through the hive with their wings when it is warm. The whole hive is a living thermostat, symmetrically organized around the care of the next generation. If you close your eyes and imagine the hum of a hive, low, warm, steady, you might find it sounds a little like the sound of your own breath. A continuous murmur, a living rhythm, a warmth that fills the space around you. The face of a human being has bilateral symmetry, and so does the face of almost every vertebrate animal, every creature with a backbone. Fish frogs, lizards, birds, mammals. The left side mirrors the right. 2 eyes, 2 nostrils, 1 mouth centered, 2 ears at the same height. This symmetry is so deeply familiar that we read slight asymmetries as signals. A drooping eyelid that suggests tiredness, a crooked smile that suggests warmth or mischief. Research suggests that the degree of facial symmetry in many animals is related to genetic health, that a highly symmetrical face develops when development goes smoothly, when the organism's genetic blueprint is expressed cleanly without interference from stress or disease. This is why, in many species, symmetry is used as a signal in mate choice. The peacock's tail, fanned out behind it like a great circle of eyes, is perhaps the most extravagant example. Each eye spot on each feather is bilaterally symmetrical, and the whole display is radially symmetrical. And a peahen observes all of this with quiet attention before deciding. But it is not just mate choice. Baby ducks follow their mother because she is the largest symmetrical moving object they encounter in the first hours of their lives. Young animals of many species are drawn instinctively to symmetrical forms. We are all, from the very beginning, reading the language of balance. Outside, somewhere in the warm dark, a firefly is lifting off from a blade of grass, its light blinking at precisely timed intervals, its wings beating in perfect bilateral coordination. It rises and falls, and rises again, a small symmetry traveling through the night air. The segments of a caterpillar's body are another kind of symmetry, not left mirroring right only, but also front echoing back, each segment a repetition of the last, each one carrying the same basic plan of legs and breathing holes and muscles. This repetitive segmental symmetry is called serial homology, and it is the body plan of all insects and many other invertebrates. You can see it most clearly in a centipede moving across leaf litter, each pair of legs lifting and falling in a wave that moves from front to back. A caterpillar moves by sending waves of muscle contraction along its body from back to front, each segment contracting in turn. If you watch one long enough, and they move slowly enough that this is quite easy to do, you can see the wave of motion traveling through the body with a kind of meditative regularity. Front, middle, back, and again. And then, in its chrysalis, the caterpillar dissolves most of its body into a kind of living soup and reorganizes itself into something entirely different, something with wings, with a new kind of symmetry, with a new way of moving through the world. The same genetic instructions that once built a segmented crawling thing now build a bilaterally symmetrical flying one. The symmetry changes, the beauty remains. Let your body feel heavier now. Let your legs feel long and still. You're not going anywhere tonight. You're just here, breathing, listening, resting. If you are finding these stories helpful for winding down at the end of the day, we would love for you to check out the playlist. There are many more quiet journeys through the natural world waiting for you there whenever you need them. The flowers of the orchid family are among the most bilaterally symmetrical and also the most varied in all of plant life. There are more than 28,000 species of orchid, more than any other flowering plant family. And almost every one of them has that single line of symmetry, that one way to fold and find a match. The lip of an orchid flower, the petal that droops down and forms a landing platform for pollinators, is always on the bottom. Always. In almost every orchid species on Earth. This is because the flowers rotate as they develop, a process called resupination, twisting themselves into the right orientation before they open. This consistent, persistent orientation means that every orchid in the world, from the vanilla orchid of Mexico to the ghost orchid of European swamps to the lady's slipper of English woodlands, shares a fundamental symmetry. They have diversified into an almost incomprehensible variety of forms and colors and structures. And yet, all of them are recognizably orchids. All of them are organized around the same quiet plan. Some orchids mimic the appearance of female insects so precisely that male insects attempt to mate with them, picking up pollen in the process. The mirror orchid of the Mediterranean has petals that not only look like a female bee, but reflect ultraviolet light in the same patterns that the bee herself produces. The male bee is drawn to the flower by sight, by scent, by something that must feel to him like the most real thing in the world. And then he finds himself carrying pollen to the next flower. The symmetry here is not just visual, it is a symmetry of relationship, a perfect balance between deceiver and deceived. Rest now. Let everything settle. The orchids are blooming in the dark, each one turned precisely the right way. Everything is where it needs to be. There is a starfish somewhere on the ocean floor right now, moving so slowly you would have to watch it for minutes to be sure it was moving at all. It is traveling across the sand on hundreds of tiny tube feet, each one operated by a small hydraulic pressure of water, and if you looked at it from above, you would see its 5 arms radiating outward from the center with the most perfect 5-fold symmetry. Each arm identical to the next, each one capable in most species of regenerating into a whole new animal if separated from the body. 5-fold symmetry is unusual in the living world. Most radially symmetrical animals have 4-fold or 6-fold symmetry. The echinoderms, the group that includes starfish, sea urchins, sand dollars, and sea cucumbers, chose 5, and they chose it very early, something like 500 million years ago, and they have stuck with it ever since. No one is entirely certain why. 5 is a prime number, which means you cannot divide it into smaller equal groups. Perhaps there is some structural advantage to this indivisibility. Perhaps it is simply one of nature's quiet preferences. A sand dollar lying on a beach shows this 5-fold symmetry in the most elegant way. The top of the shell bears a design that looks like a 5-petaled flower. This is where the tube feet once emerged, through 5 pairs of pores arranged in the petal pattern. Pick one up and hold it gently. It is extraordinarily light. It is the most delicate geometry, whitened by the sun. Let your breath slow to the pace of the tide. In and out, in and out. The veins of a leaf form a branching pattern that, if you trace them carefully, reveals its own kind of symmetry. From the central midrib, secondary veins branch outward at regular angles, and from those, smaller veins branch again, and from those, smaller still, until the leaf is filled with a lattice so fine you cannot see the individual threads without magnification. This branching symmetry, the same pattern repeating at smaller and smaller scales, is a kind of fractal. A fractal is a shape that contains copies of itself at every scale. The coastline of a country is fractal. Zoom in on any section, and you find more bays and peninsulas, and zoom in on those, and you find still more. The branching of a tree is fractal. The way the trunk divides into main branches, which divide into smaller branches, which divide into twigs, which divide into smaller twigs, following the same branching angle all the way down to the smallest twig that holds a bud. The branching of rivers seen from above is fractal. The branching of lightning, the branching of your own circulatory system, the arteries that branch into arterioles, that branch into capillaries, the same pattern of division carrying blood to every cell in your body. The lungs, too. The bronchi branch and branch and branch until they reach the alveoli, tiny air sacs where oxygen crosses into the blood, and this branching maximizes surface area within a constrained volume. The same logic as the hexagonal honeycomb, the same patient optimization that nature returns to again and again. You are, it turns out, full of fractal symmetry. Every breath you take is a journey through a branching fractal tree that ends in 300 million tiny spheres, each one smaller than a pinhead, each one doing its quiet, necessary work. Take a breath and feel the tree of your lungs expand. Then let it fall. It has been doing this perfectly every moment of your life. The symmetry of a bird in flight is one of the most moving things to watch on a calm afternoon. A heron lifting off from a shallow lake spreads wings that are identical in their reach and curve, each primary feather a mirror of the corresponding one on the other side. The flight feathers are arranged with such precision that the wing works like a single efficient airfoil, each feather adjusting slightly to manage turbulence. Birds preen their feathers for hours each day, running each feather through their beak to zip up the tiny barbules, the hooks that hold the feather's surface together, and to apply oil from a gland at the base of the tail. This is not vanity. A feather with broken barbules is an asymmetrical feather, and an asymmetrical feather creates drag, disrupts airflow, costs the bird energy. The symmetry of a bird's wings is maintained with the same careful attention that an engineer brings to an aircraft. More careful, in fact. The bird began this work long before we did. The migration of birds involves symmetry in time as well as space. The same routes followed year after year, the same timing adjusted for the same weather patterns. There is a symmetry in the returning. The swallows that come back to the same barn, the salmon that find their way back to the same stream, the whales that travel the same ocean corridors between feeding grounds and breeding grounds. The world has grooves in it, worn smooth by millions of repetitions, and living creatures follow them back and forth across the seasons. It is very pleasant to think about this. In the warm dark, the swallows are somewhere south of here, in their winter home. They will come back. They always come back. The shells of mollusks, snails, clams, mussels, nautiluses are among the most diverse and beautiful objects in the natural world, and almost all of them are built on symmetrical principles. A clamshell has bilateral symmetry. The two halves, the two valves, mirror each other along their shared edge. A snail shell has a helical symmetry. It spirals, and the spiral is consistent in its proportions from beginning to end. Most snail shells spiral clockwise when viewed from the apex, the pointed top of the shell. This is called dextral winding, or right-handed. A very small number of species spiral counterclockwise, sinistral, or left-handed. And occasionally, Within a predominantly right-handed species, a single individual is born with a left-handed shell. This individual will have great difficulty mating because the geometry of mating in snails depends on the matching of shells, and a left-handed shell cannot easily align with a right-handed one. There is something poignant and extraordinary in this, that the direction of a spiral, barely perceptible, shapes an entire life. Nature takes its symmetry seriously. If you enjoy these gentle journeys through the hidden patterns of the world, please feel free to drop a comment below. We read everyone, and they bring a lovely warmth to this quiet space. Now, let's drift on. The stripes of a zebra are perhaps the most famous pattern in the animal kingdom, and they are arranged with a bilateral symmetry that perfectly mirrors across the center line of the body. The left side is the mirror of the right, but the stripes of each individual zebra are unique. No two zebras have exactly the same pattern, any more than two human fingerprints are the same. The symmetry is the rule. The variation is the life inside the rule. The stripes of a zebra are thought to serve several purposes. They may confuse predators by making it hard to isolate a single individual from a moving herd, or they may deter biting flies, which seem to prefer unpatterned surfaces. But they also help zebras recognize each other. Each animal in a herd knows the others by their stripes, the way we know a face. The symmetry makes a pattern. The variation makes it personal. Tigers, too, have bilaterally symmetrical stripes. No two tigers have identical patterns. The stripes on a tiger's forehead sometimes form a character that, in Chinese, means king. This is coincidence, or perhaps it is one of those moments where the patterns of nature and the patterns of human meaning happen to overlap briefly, like two pools of light touching. Let the thought of a tiger settle quietly in your mind, not the fierce thing, but the resting thing, lying in dappled shade, its striped sides moving slowly with each breath, its eyes half closed. The branching of a tree against a winter sky makes a pattern that is, if you stand far enough back, bilaterally symmetrical. The left side of a well-grown oak roughly mirrors the right, each major branch answered by a corresponding one on the other side, the whole canopy spreading in a shape that distributes light-catching leaves as evenly as possible across the space available. Trees that grow in the open, with light coming equally from all directions, tend toward a rounded, radially symmetrical canopy. Trees that grow at the edge of a forest, with more light on one side, grow asymmetrically toward the light, the symmetry broken by the asymmetry of the environment. In this way, a tree is a record of its history. Its shape tells you something about where the light was, year after year, as it grew. The asymmetries in a tree's crown are a kind of autobiography, but the internal structure of wood, the growth rings, the arrangement of vessels that carry water from roots to leaves, is radially symmetrical around the central pith. The tree grows outward from its center in all directions equally, adding a new layer of wood each year. In the cross-section of a log, you can count the years. You can see the wide rings of good wet years, the narrow rings of drought. The symmetry is the frame. The variation is the record of time. It is growing late. Let your eyes feel heavy. Let the day that is ending feel finished and settled, like a ring of growth sealed inside the heartwood of a tree. Complete, whole, done. The ocean is full of symmetry, not in the restless surface of waves, which seem random and wild, but in the creatures that live beneath it. and in the patterns of current and depth and light. A jellyfish is radially symmetrical. Its bell, its trailing tentacles, its internal organs all arranged around a central axis. Most jellyfish have fourfold or eightfold symmetry. The moon jellyfish, that most common and ghostly of ocean visitors, has a fourfold symmetry that you can see through its translucent bell. 4 horseshoe-shaped gonads, 4 oral arms, arranged in a perfect cross. A jellyfish moves by pulsing, contracting its bell to push water backward, then letting it relax and refill. The pulse is symmetrical. Every part of the bell contracts at the same time. Every part relaxes at the same time. The creature breathes and moves and lives in perfect radial balance, drifting through the water with a patience that has changed very little in 600 million years. Jellyfish are among the oldest animals on Earth. They were here before the dinosaurs. They will, in all likelihood, be here long after us. They have no need to hurry. The ocean itself is organized by symmetry of a larger kind. The great ocean gyres, the vast, slow, circular currents that move warm water from the tropics toward the poles and cold water back again, are arranged with a rough bilateral symmetry across the equator. The North and South Pacific each have a gyre. The North and South Atlantic each have one. They rotate in opposite directions, clockwise in the north, counterclockwise in the south. Mirror images of each other, driven by the same forces of wind and Earth's rotation, organized by the same deep planetary geometry. Let the thought of the ocean carry you. Let it be very large and very quiet around you, and you very small and very still in the center of it. The symmetry of a raindrop is something most people have never thought about, because we imagine raindrops as the teardrop shape of a cartoon, tapering at the top and rounded at the bottom. But a real raindrop falling through air is not shaped like that at all. A very small raindrop is nearly perfectly spherical, the most symmetrical shape that exists in 3 dimensions. The shape where every point on the surface is exactly the same distance from the center. A larger raindrop is flattened by air resistance into something more like a lens, flat on the bottom, domed on top, but still perfectly symmetrical around its vertical axis. The sphere is the shape that minimizes surface area for a given volume. Water, held together by the surface tension of its molecules, naturally seeks this shape. A dewdrop on a leaf, if the leaf is hydrophobic, water repellent, will bead up into a near-perfect sphere, sitting on the surface like a tiny planet. In the morning light, it refracts the world around it into a tiny inverted image, a complete picture of everything, curved and miniaturized, held in a drop of water. There is something almost miraculous in this. The entire scene, the leaf, the light, the sky, captured in a sphere of water smaller than a pea, hanging from a blade of grass, the world reflected in perfect symmetry. The flight of a murmuration, a flock of starlings moving through the evening sky, seems at first like pure chaos, like random noise. But watch it for a little while, and you begin to see a kind of symmetry in the motion. The flock contracts and expands, rolls and turns, and through all of this movement, it maintains a roughly constant density. The birds are never too close, never too far apart. Each bird is responding to the movements of its nearest neighbors, and the result is a flow that looks like fluid, like water, like smoke, continuous, smooth, organized without a leader. The symmetry here is not the static symmetry of a snowflake, but the dynamic symmetry of a living system in balance. The flock is a kind of symmetry in time, the same patterns appearing and disappearing and reappearing, the same response to disturbance, the same return to equilibrium. It is the symmetry of a river finding its level, of a pendulum settling into its swing. The starlings are flying now, somewhere over a darkening field. They are turning together, thousands of them, making shapes in the sky that have no name. You do not need to see it to feel it. Just let the thought of it be somewhere nearby, warm and alive. The Romanesco broccoli, which you may have seen in a farmer's market or a health food store and wondered about because it looks almost too perfectly strange to be real, is one of the most visually striking examples of natural fractal symmetry. Its head is a spiral made of smaller spirals, each of which is made of still smaller spirals, all of them following the same Fibonacci pattern as the sunflower, all of them the same pale green, the whole thing looking as though it were grown by someone who had been thinking very carefully about mathematics. It is, in a way, the same genetic programs that guide all plant growth, the same hormonal signals, the same cellular divisions following the same branching rules, produce this extraordinary object when given the right conditions. The Romanesco is not a carefully crafted exception. It is what happens when ordinary plant growth rules operate with particular precision. It is nature's geometry made visible. If you have ever cut a head of broccoli or cauliflower and noticed that the florets on the inside look like smaller versions of the whole head, you have noticed a fractal. Most brassicas, the plant family that includes broccoli, cauliflower, cabbage, kale, have this self-similar structure to some degree. The Romanesco just makes it impossible to ignore. Please, if you find yourself with a warm blanket and a very quiet mind, do like this video. It means the world to us and helps other sleepy people find their way here. Now, let's continue. The ice crystals that form on a cold window in winter are some of the most accessible and intimate examples of natural symmetry. They grow directly on the glass as water vapor from the air freezes onto the cold surface, and they grow in branching fern-like patterns called dendrites, the same word used for the branching projections of nerve cells because they have the same fractal, tree-like structure. Unlike the six-fold symmetry of snowflakes falling through the air, window ice crystals grow in 2 dimensions, spreading across the surface of the glass, and their symmetry depends on the surface they grow on and the conditions in the room. But even so, you will often find bilateral symmetry in individual crystal branches, left mirroring right, each side growing at the same rate in the same way. If you have ever pressed your face close to a frosted window and breathed on it, watching the crystals melt in a circle of warmth around your breath, you have dissolved a very old and very precise geometry. Your breath, carrying warmth and moisture, returned the ice to water, returned the pattern to the formless. And then the cold air came back and the crystals grew again. Always, they grow again. The stars of the sky have their own symmetry, not the bilateral symmetry of a leaf or the radial symmetry of a flower, but the symmetry of reflection across very large distances. The Milky Way, that river of light that crosses the sky on dark, clear nights, is a disk galaxy, and it is roughly symmetrical above and below its central plane. Our solar system sits within this disk, about 2/3 of the way from the center to the edge, and when we look toward it, the center of the galaxy, we see more stars, the dense, bright core. When we look away, we see fewer, the edge of the disk, the beginning of the intergalactic dark. The spiral arms of the Milky Way curve outward from the center with a rough rotational symmetry. Not perfect, because galaxies are not perfect, because gravity is a complicated thing, and because the galaxy is billions of years old and has had many collisions and distortions. But the broad pattern is there. Spiral symmetry, the same logarithmic spiral as the Nautilus shell, the same Fibonacci proportions, on a scale that takes light 100,000 years to cross. We are inside it. You, right now, lying or sitting in the dark, are inside a spiral galaxy that follows the same mathematical principles as the shell of a snail on the ocean floor. The geometry goes all the way up and all the way down. We live inside a pattern and on top of a pattern and among patterns that contain patterns. And in the very middle of all of this, there is you, breathing, resting, belonging. Let that settle. Let it be a weight that is not heavy. Let it be the kind of largeness that makes small things feel safe. Sleep is coming. Can you feel it? Like the turning of a slow spiral, like the deepening of a quiet color, like the edge of a snowflake growing in the dark. The face of the moon, as you have always known it, is a kind of symmetry, not perfect, not mathematical, but the symmetry of something familiar, seen from the same angle for so long that it has become part of the vocabulary of night. The moon always shows us the same face because it rotates once for every time it orbits the Earth, a gravitational synchrony called tidal locking that has made the far side of the moon unknown to all human eyes until the first spacecraft went around it in 1959. The near side of the moon, the one you see rising, the one that lights the ground on a clear night enough to walk by, is marked by great dark plains called Maria, which early astronomers mistook for seas. Mare Tranquillitatis, the Sea of Tranquility. Mare Serenitatis, the Sea of Serenity. The names are still there, and the dark patches are still there. And even though we know now they are ancient basaltic plains formed by long-cooled lava, the names still feel right. They do feel like seas. They feel calm. The moon, looking down, feels calm. Let the light of the moon, even imagined, fall on your face. Let it be cool and silver and still. The symmetry of a bee's body is the symmetry of all insects. Bilateral from head to tail, segmented along the length, with wings that fold away with perfect engineering. A honeybee in flight beats its wings 200 times per second, and both wings on each side move together, held in coordination by tiny hooks, hamuli, that lock the forewing and hindwing of each side into a single flight surface. In the hive, a worker bee lives for about 6 weeks in summer. She performs many jobs in that time: cleaning cells, nursing larvae, building comb, guarding the entrance, foraging for nectar and pollen. Each job has its own symmetrical rhythms. The guard bees at the entrance face outward, vibrating their wings to fan the air, checking each returning forager by scent. The nurse bees move from cell to cell in a pattern so regular it looks choreographed. The queen moves through the comb-laying eggs, one per cell, precisely, never missing, never doubling, an egg placed with the symmetry of a machine and the intention of a living creature. Bees communicate direction and distance through a dance, the waggle dance, in which a forager returning with news of a good flower source runs a figure-8 pattern on the comb, waggling her abdomen on the straight run. The angle of the straight run relative to vertical tells the other bees the direction of the flowers relative to the sun. The duration of the waggle tells the distance. It is symmetrical information, encoded in symmetrical motion, read by creatures who understand it perfectly. The figure-8 pattern of the waggle dance is itself a kind of bilateral symmetry, each loop of the 8 mirroring the other, the straight run bisecting the middle. The bee is drawing the shape of her journey in the air of the hive, and the other bees are reading it in the dark. The honey-guide bird of Africa has a relationship with honey badgers, and sometimes with humans. That is one of the most extraordinary examples of interspecies cooperation in nature. The honey guide knows where beehives are, but cannot open them. The honey badger, or the human, can open them, but does not always know where they are. So the bird leads the way, flying ahead, calling, waiting, flying ahead again, until the stronger creature has broken open the hive. Then both share the reward. The bird gets the beeswax and larvae at once. The badger gets the honey. There is a symmetry in this partnership, each providing what the other lacks, each benefiting from what the other provides. The world is full of these symmetries of need and gift. The fig tree and the fig wasp, each unable to reproduce without the other. The cleaner fish and the large predator who holds still to be deparasited and does not eat the small fish doing the cleaning. The mycorrhizal fungi in the soil and the trees above, exchanging minerals for sugars in a network that stretches for miles beneath a forest floor. We are part of these symmetries too, though we often forget it. The air we breathe out is what the trees breathe in. The night feels large and quiet, and in the quiet, all these exchanges are happening, perfectly balanced. In the dark, we are so glad you are here with us tonight. If you have found your way to this channel for the first time, please have a look at the playlist. There are many more stories waiting for you, each one a gentle journey through some quiet corner of the natural world. The rings of Saturn, seen through even a small telescope, are one of the most symmetrical objects visible in the night sky. They spread outward from the planet's equator in concentric bands, an inner ring, a gap, an outer ring, the faint gossamer rings beyond. And the whole system is bilaterally symmetrical across the plane of the rings. The planet sitting at the center, like a word in the middle of a sentence. Saturn's rings are made of ice and rock, from tiny grains to boulders, all orbiting the planet at different speeds, kept in their lanes by the gravity of Saturn and by the gravitational influence of several small moons that orbit within the ring system. These shepherd moons keep the edges of the rings sharp, herding stray particles back into line. The rings are alive with subtle dynamics, waves, spirals, gaps, all of it organized by gravity into a kind of slow, cold, symmetrical dance. The rings are not permanent. They are, on a cosmic timescale, a temporary thing. Perhaps a few 100 million years old, perhaps only lasting another 100 million years before they spiral inward into the planet. A visitor who came to this solar system at a different time might find Saturn ringed or not ringed. We happen to be here while the rings are here. This feels in a quiet way like a gift. A river delta, seen from above, resembles a hand, a spreading network of channels branching outward from the main river into the sea or lake, each channel smaller than the last, all of them carrying water and silt toward the waiting water. The Nile Delta, the Mississippi Delta, the Ganges-Brahmaputra Delta, all of them branch in this fractal, hand-like way, all of them building new land grain by grain at the edge of the water. The delta is where the river finally slows down enough to let go of what it has been carrying. A fast river carries sediment in suspension, the particles held up by turbulent flow. When the river meets still water and slows, the particles fall. First, the heaviest, sand and gravel, then silt, then fine clay. Layer by layer, grain by grain, the delta builds. The symmetry of a delta is the symmetry of accumulated time, of 10,000 floods each, leaving a thin signature in the mud. The soil in a delta is some of the most fertile in the world. The great river valleys, the Nile, the Indus, the Tigris and Euphrates, the Yellow River, are where the earliest human civilizations grew, precisely because the rivers kept bringing new fertility down from the mountains and laying it gently on the floodplains. Our oldest cities are built on symmetry, on the symmetry of a river that gives and gives and gives. Let yourself feel the weight of all that giving. Let yourself feel received. The chrysanthemum in Japanese culture is a symbol of the sun, of long life, of the emperor. Its flower is radially symmetrical, petals radiating outward from the center in a perfect circle, layer upon layer of them, each layer echoing the last. The chrysanthemum has been cultivated in China for more than 2,500 years, and in that time, breeders have extended and elaborated its natural radial symmetry into forms of extraordinary complexity. Flowers with hundreds of petals curling in every direction, still organized around the same central axis, still following the same radial plan. The Japanese mon, the heraldic symbols used by samurai clans and still used today by institutions and businesses, frequently features the chrysanthemum. The imperial family of Japan uses a 16-petaled chrysanthemum as their seal. It is one of the most symmetrical symbols imaginable. A perfect radial design, every petal exactly like the last. No beginning and no end to the circle it makes. But the wild chrysanthemum, the ancestor of all these cultivated forms, is a simpler thing. A single ring of white or yellow petals around a golden center, like a daisy, like the sun it is named for. And it is beautiful in its simplicity, in the plainness of its symmetry, in the way it sits in a late autumn field, looking entirely unconcerned about anything at all. That is a very good thing to aspire to in the last quiet moments before sleep, to sit in the autumn light, looking entirely unconcerned, symmetrically at peace. The world beneath our feet is organized in ways we rarely think about, because it is mostly invisible to us. But the soil is full of its own quiet symmetry. The roots of a plant spread outward from the base of the stem in branching patterns that mirror, below ground, the branching of the leaves above. The tree, in this way, is symmetrical in a vertical sense. The canopy above and the root system below are approximate mirrors of each other, one reaching toward light, the other reaching toward water and minerals. The mycorrhizal network that connects the roots of trees in a forest to each other through fungal threads is organized with its own kind of symmetry. Each tree connected to its neighbors, the network as a whole, roughly reflecting the distribution of trees above. Older trees at the center of the network tend to be more connected. They have had more time to establish relationships with the fungal threads, more time to send carbon sugars down through their roots in exchange for phosphorus and water coming up from the soil. The network flows constantly in both directions, giving and receiving, the symmetry of exchange. This network has been called the Wood Wide Web, and while that name perhaps overstates the intentionality involved, the trees are not exactly communicating the way you and I do. It does capture something true about the structure of a forest. It is not a collection of individuals. It is a community, organized around flows of resource, balanced by mutual dependence, symmetrically interconnected. Let yourself be connected right now to the weight of the earth below you and the air above you and the soft sounds of the world around you. You are inside something very large and very calm. The scales of a fish are arranged in overlapping rows, each scale a curved, roughly symmetrical shape, the whole pattern tiling the body like flexible armor. The scales of a carp, seen in good light, have a beauty that is easy to miss, each one slightly iridescent, the rows following the curve of the body, the whole fish a moving, shimmering pattern of interlocking symmetries. Fish scales grow throughout the fish's life, and like the rings of a tree, they record that growth in concentric rings. The rings are closer together in winter when the fish grows slowly, and further apart in summer when growth is faster. A scientist can age a fish by counting these rings, called circuli, under a microscope. The symmetry of a fish scale is a clock, a diary, a record of years lived in water. The lateral line of a fish, the row of sensory cells running along each side from head to tail, is one of the most perfectly bilateral things in the natural world. One line on the left, one on the right, exactly symmetrical, detecting pressure waves and vibrations in the water. A fish feels the approach of another creature through its lateral line before it sees it. The water trembles, and the line trembles with it, and the fish knows what is coming before it arrives. The puffer fish, that strange and small-eyed creature of tropical waters, builds one of the most extraordinary symmetrical structures in the animal kingdom. The male white-spotted puffer fish spends about a week constructing an enormous circular nest in the sand on the ocean floor, using only his fins and his body. The finished nest is a mandala, a circular pattern of ridges and valleys, perfectly radially symmetrical, about 2 meters across. The ridges are decorated with shell fragments, arranged to create the finest possible texture. The whole structure is built entirely by one small fish, entirely underwater, entirely without tools, and it is so precisely symmetrical that it was first observed by divers who could not believe it was natural. But it is. It is the most precise architectural symmetry built by any non-human creature. The female pufferfish swims to the center of the nest, lays her eggs, and leaves. The male cares for the eggs, fanning them with his fins. And then, The nest gradually disperses in the currents, and the male begins again somewhere new. If you would like to tell us in the comments what surprised you most so far tonight, we would genuinely love to know. But there is no rush. You can always do it in the morning. For now, just breathe. The spider plant, which sits on the windowsills of many homes, produces runners, long stems that arch outward from the main plant and develop small plantlets at their tips. These plantlets hang in the air, symmetrically arranged around the parent plant, each one a complete miniature version of the whole. When they are allowed to touch soil, they root and become independent plants. The parent plant reproduces by sending out miniature copies of itself in all directions. The symmetry is radial, the multiplication is fractal. The windowsill becomes a very slow explosion of green. The peace lily, that other common houseplant, produces a white flower that is actually not a flower, but a spathe, a modified leaf folded around the true flowers within. The spathe is perfectly bilateral, one side folding up and over as a smooth white hood. The structure it shelters is a spadix, a column of tiny true flowers, radially symmetrical around its axis. One plant, two kinds of symmetry, one gesture of quiet beauty on a table in an ordinary room. Plants have been making their way into human spaces for as long as humans have had spaces. This is not an accident. We respond to them, to their symmetry, to their greenness, to their livingness, in ways that seem to be very old and very deep. A room with a plant in it feels different from a room without one. Perhaps it always has. The way clouds form has its own symmetry. Cumulus clouds, the great white piles that drift on sunny days, grow by convection, warm air rising, cooling, condensing into water droplets. They tend to be roughly circular in their base because the rising column of warm air is roughly circular. From directly below, a cumulus cloud looks like a circle. From the side, it looks like a dome, rounded on top, flat on the bottom, the flatness marking the level at which the rising air reached the right temperature to condense. Cirrus clouds, the thin, high wisps, are formed when ice crystals grow in the upper atmosphere and then fall through different wind layers, leaving trails. The trails curve and hook and fan in patterns that look almost like brush strokes, almost like the most minimal writing. There is a bilateral quality to many cirrus formations, the hooks on either side of the cloud forming symmetrically, the way a feather forms. A lenticular cloud, which forms when moist air flows over a mountain and is forced upward, is one of the most symmetrical objects in the sky. It forms in a stable lens shape, smooth, rounded, perfectly symmetrical around a horizontal axis, hovering over or near the mountain peak as new air constantly flows in from one side and out from the other. From a distance, a lenticular cloud looks so precisely formed, so still against the moving sky around it, that it has been mistaken for many things. But it is just air and water, organized by the invisible geometry of airflow, maintaining its perfect lenticular shape for as long as the wind holds the right conditions. The night sky, where we began with the moon and the stars, is itself a kind of symmetry. The great circle of the visible horizon, the dome of the atmosphere curving overhead, the stars scattered across it in patterns that our ancestors found faces and animals and heroes in, because we are very good at finding patterns, because our minds are built for symmetry, because recognizing a familiar shape in the chaos is one of the oldest and most useful things a mind can do. The constellations are not real groupings. The stars in Orion, say, are not near each other in space. They just appear in the same direction from Earth. But the patterns we have found in the sky are real patterns in the sense that they are consistent, repeatable, findable every clear night in the same part of the sky. They are symmetrical in time. Orion rising in winter, the Pleiades in autumn, the Southern Cross for those who live beneath it. The same patterns turning overhead every year, every century, every millennium, as long as there have been eyes to look up and minds to find the shapes. Someone, thousands of years ago, looked up and found the belt of Orion and felt something. Recognition, comfort, beauty, the sense of a world organized beyond the chaos of daily life. That feeling has been passed down quietly through every generation since. You have inherited it. Tonight, it is yours. Let the sky be large above you, and let yourself be small beneath it, and let smallness feel like the safest thing in the world. It is. You are held. You are exactly where you need to be. The symmetry of the turning world is all around you, and it will continue turning gently while you sleep. The morning glory flower opens each day and closes each night, and the opening is a kind of symmetry in time, a rhythm that repeats with the faithfulness of a clock, governed by the same light that governs so much of life. The flower is also bilaterally symmetrical in its structure, its 5 petals fused into a funnel, the funnel striped with lines that guide pollinators toward the center. But the most extraordinary symmetry of the morning glory is its spiral bud. Before the flower opens, it is furled in a perfect spiral twist, the petals overlapping in a consistent clockwise or counterclockwise rotation that is specific to the species. When the flower opens, it unspirals slowly over the course of an hour in the early morning, relaxing from its coiled form into the open funnel, and when it closes at night, it re-spirals with the same turn, the same patient winding. The morning glory has been opening and closing in this way for millions of years. Each flower lasts only one day. It opens in the morning and closes and dies by evening. But the plant continues to produce new buds, new spirals, new openings. The individual moment is brief. The pattern endures. Let your breath follow a rhythm like that. Open and close, open and close. Each breath its own morning, each breath its own evening. The compound eye of an insect, a dragonfly say, or a fly, or a bee, is made of thousands of individual facets, each one a tiny lens with its own light-detecting cell beneath it. These facets are arranged in a radially symmetrical dome, curving over much of the head, giving the insect a nearly 360-degree field of view. Each facet detects a slightly different angle of the world. The insect's brain assembles these thousands of slightly different views into a single image, not quite like ours, but complete in its own way. The facets of a compound eye are hexagonal, packed together with the same efficient geometry as a honeycomb. You can see this with a good magnifying glass on a housefly or a dragonfly. The smooth, slightly iridescent dome of the eye resolves into a perfect hexagonal lattice, each hexagon a window into the insect's experience of the world. A dragonfly has been watching the world through this geometry for more than 300 million years. They were here before the dinosaurs, flying over ancient swamps on wings that have barely changed since then. The dragonfly wing, another bilateral symmetry, two pairs of wings each mirroring the other, is one of the most efficient flight structures ever evolved. It can fly in all directions, hover, spin, catch prey in midair. It does this with four wings that never need to touch the ground. The dragonfly resting on a reed at the edge of a pond, its wings horizontal and still, is one of the quietest images I know. The water below reflects its wings. The reflection and the wings together make a perfect bilateral symmetry, wings above and wings below, divided by the thin line of water surface. The symmetry of a reflection is one of the first symmetries we encounter in our lives, and perhaps the most magical. A still lake on a windless morning reflects the mountains and the trees and the sky with such precision that the reflected world seems as real as the real one. And for a moment, standing at the edge, you are at the boundary between two worlds, one above and one below, both equally complete, both equally still. Every mountain has its lake reflection self. Every tree has its water shadow. The world doubles itself in every still surface, creating a symmetry that lasts exactly as long as the wind stays away. Thank you for being here with us tonight. It means so much to know these stories are helping people find rest. If you have not yet had a chance to like the video, a small tap on that button sends the most helpful signal into the world. Now let's keep drifting. The Nautilus, which we visited briefly earlier, deserves a longer moment. The animal itself, the soft-bodied creature that lives in the outermost chamber of its shell, is bilaterally symmetrical, as most mollusks are. It has a mantle, a ring of tentacles arranged around its mouth, a kind of hood that covers its head. The tentacles, which can number 90 or more, are arranged in two groups, one on each side of the mouth, again in bilateral symmetry. The Nautilus moves by jet propulsion, drawing water into a muscular funnel and expelling it, sending itself backward or sideways or turning. It can also adjust its buoyancy by regulating the gas and fluid in its many shell chambers, rising and falling in the water column with the ease of a submarine. The Nautilus is sometimes called a living fossil, not because it has not evolved, but because its basic form has remained recognizable for 450 million years. The nautiloids of the Cambrian Sea would have looked familiar to us, the same spiral shell, the same array of tentacles, the same soft, dark eye. 450 million years. The trilobites are gone, the ammonites are gone, the great sea scorpions are gone, and the Nautilus is still here, spiraling through the dark water, the same as it has always been. There is something very restful about this kind of continuity. Not the rigid continuity of something that cannot change, but the fluid continuity of a form that has found its place and stayed in it, generation after generation, not needing to become anything other than what it is. The coral reef is a city of symmetry. Each coral polyp, the tiny animal that builds the reef, is radially symmetrical, with tentacles arranged in multiples of 6 around a central mouth. The polyp builds a cup of calcium carbonate beneath itself, and over years and decades and centuries, the accumulated cups of millions of polyps build the great branching, domed, and spreading structures we call corals. The shapes of different coral species are themselves symmetrical. Brain coral named for the rounded, grooved surface that resembles a brain, has a roughly spherical form with bilateral symmetry along its top ridges. Staghorn coral branches in a pattern that echoes the branching of deer antlers, each branch roughly symmetrical, the whole colony spreading in all directions. Table coral grows flat and horizontal like a table, creating a broad circular canopy of symmetrical architecture. The reef as a whole is symmetrical in the sense that any healthy reef ecosystem is symmetrical, balanced, in dynamic equilibrium, each species taking what it needs and leaving enough for the others. Parrotfish grazing on algae, keeping it from smothering the coral. Cleaner wrasses removing parasites from larger fish. Eels and octopuses hunting in the crevices. Tiny neon gobies resting on coral heads, waiting for customers. Everything in its place, everything in balance, the whole system as symmetrical as a wheel around its hub. A healthy reef makes a sound, a continuous crackling, snapping, popping sound, made by shrimps and fish and the general biological activity of thousands of creatures going about their lives at once. This sound is called the reef soundscape, and it is, in healthy reefs, bilaterally symmetrical in a sense, roughly the same in all directions, the same density of life, the same variety of sound wherever you turn. If you lower your thoughts toward that sound, the warm, crackling, living hum of a healthy reef in calm water, you might find it sounds a little like the hum at the edges of sleep, like the sound of your own mind beginning to let go of the day. Let go. The reef is humming. The Nautilus is spiraling in the dark water. The morning glory has closed its bloom and is waiting for morning. You are exactly where you need to be. The pine cone, sitting on its branch or lying on the forest floor, is carrying the Fibonacci sequence in its scales. If you pick one up and turn it in your hands, you can see that the scales spiral in two directions simultaneously, like the sunflower seeds, like the Nautilus chambers, like the pineapple. Count the scales spiraling one way, then the other, and you will almost always find consecutive Fibonacci numbers 8 and 13, 13 and 21. This is not coincidence or design. It is the result of how the scales grow, each one developing in the position that maximizes space and minimizes crowding, following the same cellular logic that produces spirals everywhere. The pine cone opens and closes with changes in humidity. In dry air, the scales splay open, releasing the seeds inside. In moist air, they close tightly, protecting the seeds from rain. This opening and closing is purely mechanical. No muscles, no nervous system. The scales are made of two layers of cells that respond differently to moisture, one layer expanding and one contracting. So the whole scale bends in response to the air around it. In this way, a pine cone is a hygrometer, a device for measuring humidity, made of nothing but wood and time. A forest floor scattered with pine cones is a floor scattered with tiny weather instruments, each one quietly opening and closing with the humidity of the air. On dry days, they are all open. On rainy days, they are all closed. The forest has its own distributed sensing system, symmetric in its responsiveness, every part of it receiving the same information from the same air. Let your mind rest on that image. The forest floor, the pine needles soft underfoot, the cones scattered among them, all slightly ajar in the dry autumn air. The smell of pine resin, which is sharp and clean and ancient. The growth rings of a tree trunk which we visited earlier in the context of symmetry, are worth returning to for a moment because they contain within them a record of something very large. A long-lived tree, a bristlecone pine in the White Mountains of California, say, which can live for 5,000 years, carries within its rings a record of 5,000 years of climate. Wide rings and narrow rings, light rings and dark rings, recording the warm years and the cold years, the wet years and the dry years, the years of volcanic ash that dimmed the sun, the years of exceptional rain. Scientists read these rings, a discipline called dendrochronology, and by overlapping the ring records of trees of different ages, they have extended the climate record back 14,000 years. 14,000 years of weather written in wood in the language of rings. This is the symmetry of pattern through time, the same signal, the same cause, producing the same effect in wood and in stone and in ice cores and in pollen records, all of them telling the same story from different angles. The oldest living individual tree in the world is a bristlecone pine known as Methuselah, growing somewhere in the White Mountains, its exact location kept secret to protect it. It is more than 4,800 years old. It was a seedling when the pyramids of Egypt were being built. It was already old when Alexander crossed the Indus. It has been growing, ring by ring, in the cold, dry mountain air for nearly 5,000 years, and it is still growing now. That thought is so large and so quiet that it is almost like a kind of sleep itself. 4,800 years, ring by ring. The symmetry of sound is something we feel in our bodies without thinking about it. A heartbeat is bilateral, lub-dub, lub-dub, the two sounds made by the two sets of heart valves closing in sequence, the right side and the left side of the heart working in alternation. A breath is bilateral too, in and out, expansion and contraction. The same symmetry in time as the wave on the ocean, as the morning glory opening and closing. Music, in every culture in the world, is built on symmetry. Rhythm is symmetry in time. Patterns that repeat, measures that echo each other, the beat divided and subdivided in consistent proportions. Melody is symmetry in pitch, themes that return, phrases that answer each other, the ascent that is answered by the descent. Harmony is the simultaneous symmetry of different pitches that fit together according to mathematical relationships. The song of a bird follows these principles without knowing them. A blackbird sings in phrases, each phrase complete in itself, each one slightly different from the last, but all of them organized around the same tonal center, the same habitual patterns. The blackbird does not know music theory, but it sings in the morning with a clarity and a structure that suggests something very like an aesthetic sense, a preference for certain intervals, certain rhythms, certain ways of filling the morning air. You have heard a blackbird in the morning, perhaps, or a robin, or a thrush. Let the memory of it be here with you now, in whatever quiet place you are. The song rising and falling, the morning opening around it. The structure of DNA, the molecule that carries the genetic instructions for every living thing, has a bilateral symmetry at its heart. The double helix is made of two strands wound around each other, and the two strands are complementary. Each base on one strand is paired with a specific partner base on the other. adenine with thymine, guanine with cytosine. The sequence of bases on one strand perfectly specifies the sequence on the other. This complementarity is not just aesthetic, it is the mechanism of heredity. When the cell divides and the DNA is copied, the two strands separate, and each one serves as a template for a new partner strand. The bilateral symmetry of the molecule is the source of its reproducibility, its accuracy, its reliability across billions of years. We carry this symmetry in every cell. Every cell in your body contains about 2 meters of DNA, coiled and folded into a space smaller than a red blood cell. And in that coiled, folded molecule, the same bilateral complementarity. Every base paired with its partner, the whole enormous sequence balanced on both strands, like two long mirrors facing each other, each one perfectly reflecting the other. You are made of symmetry all the way down. From the bilateral symmetry of your body to the bilateral symmetry of the molecule at the heart of every cell. Sleep is part of that symmetry too. The balance between waking and rest, between the taking in of the world and the letting go of it. Your body knows this rhythm. It has always known it. Let yourself follow it now. If you find these stories soothing, please share them with someone who needs a good night's sleep. The playlist is there, ready and waiting for whenever the night feels too long or the mind feels too loud. For now, let's drift on just a little further. The arrangement of petals in a rose is one of the most complex and beautiful spiraling symmetries in the plant kingdom. A rosebud is tightly coiled, each petal tucked beneath the next in a precise Fibonacci spiral. The innermost petals, the smallest, the outermost, the largest. As the rose opens, the spiral relaxes, the petals spreading outward from the center in a radial pattern that still echoes the original spiral. You can see the logarithmic curve in each petal's edge. The scent of a rose is another kind of symmetry, the symmetry of chemistry. The primary scent compounds in roses, geraniol, nerol, citronellol, and several others, are mirror image molecules of each other. A molecule and its mirror image are called enantiomers, and the extraordinary thing is that they often smell different. The same atoms, the same bonds, arranged in mirror image. And your nose, which is exquisitely sensitive to molecular shape, can tell them apart. The chemistry of scent is full of this mirror symmetry. Limonene smells like oranges in its left-handed form and like pine in its right-handed form. The same molecule, reflected a completely different smell. Spearmint and caraway are the same molecule in mirror image. The world smells different from different angles. The symmetry of chemistry opens into the asymmetry of experience, and a rose in a warm room fills the air with both forms, both mirror images, both halves of its molecular symphony, and the room smells like a rose, and that smell is one of the most immediate and ancient pleasures there is. Before we had words, we had that smell. Before we had cities, we had that smell. The rose has been blooming for 35 million years, and something very like this smell has been drifting on the air for most of that time. You are here, at the end of a long human story, breathing in the same air that a rose makes, in the same way your ancestors did. And it is enough. It is more than enough. It is everything. The symmetry of a dragonfly's wings, seen against the light, is one of the most intricate things in the world. Each wing is a lattice of veins forming irregular cells that fill the membrane between them, and the pattern of veining is roughly bilateral between left wing and right wing, rough front and rear. But at the microscopic level, the veins are coated with tiny cuticular structures, ridges and spines that prevent the wings from creasing, that direct airflow, that manage the inevitable flexing of a wing in flight. A dragonfly can beat its four wings independently, changing the angle and timing of each one to achieve maneuvers impossible for an airplane. It can fly forward, backward, sideways. It can hover motionless in a breeze. It can accelerate from stillness to 30 kilometers per hour in an instant. Aerospace engineers have studied dragonfly wings for insight into the design of small aircraft, and what they find is an engineering solution of extraordinary subtlety. The corrugated cross-section, the slightly twisted shape of the wing, the flexibility in precisely calibrated locations that cannot be easily improved upon. And this solution was arrived at not by calculation, but by the patient process of selection, generation after generation, over 300 million years. The dragonfly's wing is the answer that nature found to the question of how to fly well at a small scale. It is a very good answer. The surface of a calm river, seen from above, reflects the sky and the overhanging trees with a fidelity that makes the river look like a sky fallen to earth. In places where the water is clearest and deepest, the reflection is perfect, not a ripple to disturb it. The clouds moving slowly in the water just as they move slowly above it. The river becomes a mirror and the world doubles, and for a moment you cannot be entirely sure which world is which. Let that uncertainty be comfortable. Let the boundary between the reflected world and the real one feel soft and permeable. You are somewhere on the surface of that still river, neither entirely in one world nor the other, drifting between them. The symmetry of hibernation is the symmetry of the season, a rhythm that swings away from life and then swings back, wide as a pendulum, patient as a year. A dormouse curled in a ball in its nest of leaves and grass somewhere beneath the roots of an old hedgerow breathes only a few times a minute. Its heart beats very slowly. Its temperature falls close to the temperature of the earth around it. For 7 months, it will lie there, burning through fat reserves accumulated in the autumn, waiting for the warmth that will come again. And it will come. Spring always comes. The warmth reaches down into the soil, and the dormouse's temperature rises, and its heart beats faster, and it uncurls and blinks and begins to be hungry. The symmetry completes itself. The sleeping half of the year answered by the living half, the contraction answered by the expansion, the quiet answered by the busy noise of spring. We live in this symmetry too, the day and the night, the sleeping and the waking, the taking in of the world and the letting go. You are in the letting go part now. The world will be there in the morning. The morning will come with the same fidelity as spring. The symmetry of a snowfield is the symmetry of accumulation, each snowflake falling in its sixfold perfection, each one coming to rest on the ones before it, layer upon layer, until the surface is smooth and white, and so evenly covering that the landscape beneath is hidden. Every variation, the rock, the root, the rut, is filled and smoothed by snow, until the world is as flat and white and symmetrical as a blank page. Walking on new snow is one of the quietest experiences available. The snow absorbs sound. Its crystalline structure is full of air pockets that trap and dissipate the vibrations of sound waves. A snowfield is a natural acoustic anechoic chamber. The world becomes very close, very present, very still. You hear your own footsteps with unusual clarity, and nothing else. Your breath, your heartbeat, the creak of cold wood somewhere in a tree. And each footstep leaves a perfect impression. Your foot pressed into the snow, leaving its bilateral symmetry in white. Two halves mirrored across the center, the print of something alive, something warm, passing through a cold and symmetric world. If you would like to share with us in the comments the most symmetrical thing you have ever seen in nature, the moment that took your breath away with its balance and its order, we would love to read it. These comments are one of the quiet joys of making this channel, but only when you are rested. There is no hurry. The ears of a rabbit held upright are bilaterally symmetrical. Two identical curved forms, one on each side of the head, rotating independently on their bases to catch sounds from different directions. A rabbit can move its ears independently, turning one forward and one backward, catching sounds from two different places at once, triangulating the position of a sound source with the precision that allows survival. But when a rabbit is relaxed, truly relaxed, lying stretched out in a warm, sunny spot, its eyes half closed, both ears may fold back together, flat against the head, a mirror image of each other, and in that position, they signal something: safety, contentment, the absence of alarm. A rabbit with both ears folded flat is a rabbit that feels for this moment that everything is as it should be. That is the symmetry to aim for at the end of the day. Both ears down, everything as it should be. The pattern of a peacock's tail, a fan of feathers, each one ending in an iridescent eye spot, is a radial symmetry when the tail is fanned. The whole display is a semicircle of symmetry behind the bird, each eye spot positioned at the same distance from the bird's body as the corresponding one on the other side, the whole fan spreading with the perfect evenness of a geometric proof. The eye spots themselves are bilaterally symmetrical, each one a series of concentric ovals, from the outer ring of iridescent blue and green to the darker center. The color comes from microscopic arrays of melanin granules in the feather barbules, arranged in two-dimensional crystals that diffract light. The blue-green iridescence is not pigment, but structure, the same kind of structural color as the morpho butterfly, the same physics of light and lattice. A peacock displaying to a peahen is performing the most symmetrical act of courtship in the bird world. The tail fans. Every eye spot aligns. The bird shivers the feathers so that the eye spots seem to vibrate, to pulse, to float in space. And the peahen walks slowly along the line, inspecting, choosing, exercising a preference that has shaped the peacock's tail over millions of years of selection. The extraordinary thing is that the peahen prefers tails with more eye spots, with more symmetry, with greater bilateral balance. And so the tail keeps growing with each generation toward a greater and greater symmetry. The peacock is, in a sense, still being shaped by the preference for balance, still moving in the direction of the most perfect display. We too are still becoming. We too are drawn to symmetry, to balance, to the feeling that something is exactly as it should be. And in the quiet before sleep, when the day has settled and the night is full around us, we might find a moment of that feeling, of something being just right, just balanced, just enough. Rest in that feeling now. Let it hold you. The way light moves through water has a symmetry that is one of the most beautiful things to watch in the natural world. When sunlight enters a clear, shallow body of water, a pool, a lagoon, a shallow tropical sea, it refracts and scatters, and on the sandy bottom, it creates moving patterns of light and shadow called caustics. These patterns are not random. They follow the same physics of light, bending through a curved surface, and they have a kind of dynamic symmetry. Always the same general character, always the same family of shapes, the bright lines and shadows weaving and crossing in a pattern that has a mathematical structure beneath its apparent randomness. If you have ever lain beside a swimming pool and watched the light patterns on the bottom, or snorkeled in a clear, warm sea and looked up at the light coming down through the water, you have seen caustics. They are one of the most hypnotic natural phenomena there is. Endlessly changing, endlessly patterned, too complex to follow, and too beautiful to look away from. They are symmetry in motion, always almost the same and never exactly the same. Like music, like breath. The light in a forest has a different quality. It comes down through the canopy in patches, snowflakes, that move as the wind moves the leaves, brightening and dimming on the forest floor, spotlighting first a fern, and then a mushroom, and then a patch of bare earth. The movement of snowflakes across the forest floor has been studied by biologists interested in how plants manage their light intake. And what they find is that the flickering, intermittent light of a snowflake is actually more useful to many forest plants than steady, dim shade would be. The brief bursts of full sunlight trigger photosynthesis at full rate, even for a few seconds. And these bursts add up over a day to more energy than steady, dim light would provide. The forest floor, in other words, is optimized for the light that moves. The plants have adapted to the symmetry of flickering. The same burst, followed by shadow, followed by burst, over and over, all day, every day. They have built their photosynthesis around a rhythm. Everything in nature finds its rhythm, and every rhythm is a symmetry in time. Your heartbeat, the seasons, the tides, the migration of birds, the opening and closing of flowers, the rising and the setting of the sun. All of these are symmetries, patterns that repeat, that swing away and return, that create a world that can be counted on to do what it has always done. Your breath is one of these rhythms. Breathe in, breathe out, in, out. This is the oldest symmetry in your body, the one that has been happening since the moment you were born, the one that will continue faithfully all through the night. You don't have to think about it. You never have to think about it. It just keeps going, perfectly symmetrical, perfectly reliable, while you sleep. The lichen on a stone is one of the oldest and most patient symmetries in the living world. A lichen is not a single organism but a partnership. An alga and a fungus living together, each one providing something the other needs. The fungus provides structure and retains water. The alga photosynthesizes, providing sugars. Together, they can survive on bare rock in conditions that would kill either of them alone. Extreme cold, extreme dryness, intense UV radiation. A lichen grows outward from its center at a rate of about 1 millimeter per year. or less. A lichen the size of a dinner plate may be 1,000 years old. Its growth is radially symmetrical. It spreads in all directions at the same rate, creating a roughly circular patch. The oldest known lichens may be several thousand years old, growing on rocks in Antarctica or the high Arctic, unchanged by the passage of time, recording in their slow growth the stability of a world that does not need to hurry. A rock covered in lichen, orange lichen, yellow lichen, gray-green lichen, is a painting made over centuries, each color a different species, each one spreading its patient circle outward from where it first took hold. The rocks of an old churchyard, or an ancient stone wall, or the boulders at the edge of a mountain tarn, are galleries of this slow art. If you sat beside them for long enough, really long enough, you would see the lichens moving very slowly toward each other, toward their own gentle symmetry. We are glad you are still with us, and we hope your eyes are growing heavy and your breathing has grown slow. The playlist is there when you need it again, full of more nights like this one, more slow journeys through the world's quiet patterns. The symmetry of a spider's web, seen in the early morning covered in dew, is one of the most precise and transient beauties in the natural world. Each drop of dew sits at the junction of silk threads, and the threads between the drops are beaded with smaller droplets, evenly spaced, like the most regular string of tiny pearls. The dew reveals the structure of the web, the radial threads and the spiral capture threads, and for an hour or two, until the sun dries it, the whole construction is made visible, a radial symmetry of silk and water hanging in the cold air. The spider that built it may be waiting at the center or hidden at the edge. She built the web in the dark in an hour or two, using instinct and proprioception, the sense of where her own body is in space, to maintain the correct angles and spacings. Each radial thread is laid first, anchoring to a fixed frame of non-sticky silk. Then, the spiral threads are added from the center outward, each one touching each radial thread and sticking to it with the spider's special adhesive spiral silk. The result is a structure that can stop and hold insects much larger than the spider herself, and that absorbs the impact without breaking, because the silk stretches before it snaps. Spider silk is, by weight, stronger than steel and tougher than Kevlar. It achieves this not through hardness, but through elasticity. It can stretch to 4 times its length before breaking. This combination of strength and flexibility is the holy grail of materials science, and so far, no one has found a way to manufacture spider silk in quantity. The spider does it in her own body, from the protein she takes in with her food, and she makes it look easy. In the morning dew, the web glitters, the spider waits, the symmetry holds. The symmetry of a stone, smooth and oval in the hand, is the symmetry of patient erosion. A river stone has been carried in the current, rolled along the bed, tumbled against other stones, for years or decades or centuries, each collision rounding off an edge, each revolution smoothing a surface, until the stone has arrived at the most stable form, the one with no projections to catch the current, no edges to be worn, the form of least resistance, which is the smooth oval. Hold a smooth river stone in your mind now. Feel its weight, which is comfortable and cool. Feel the smoothness that is the accumulated work of water and time. It is a thing that has been shaped by something far larger and far more patient than anything we could bring to bear. And the result is perfect in its simplicity, bilateral in its basic form, smooth in every direction. The stone will be there in the morning, the river will be there. The water will still be moving, still carrying smaller stones toward their eventual smoothness, still doing the same work it has always done. You have been carried too, by the day, by the season, by everything that has happened and everything that has not happened. And like the stone, you have been smoothed in places. And in the smooth places you are most yourself, most rounded, most finished, most at rest. Let the weight of the stone be in your hands, and let your hands relax, and let the stone rest beside you on the bed of the river, and let the water move over everything with its constant patient sound. Sleep now. The symmetry of the world will continue without you for a while. It always does. And in the morning, it will still be there, the six-fold snowflake, the Fibonacci spiral, the mirror wings, the fractal tree, the still water reflecting the sky. All of it, patient, balanced, waiting. The way a flock of birds lands in a field has a symmetry that is easy to miss because it happens so quickly. The birds approach in a loose formation, and as the first ones touch down, they spread slightly, and the ones behind them land nearby, each one spacing itself relative to the others, until the whole flock has settled on the grass in a pattern that has no leader and no plan, but is nevertheless organized, roughly even spacing between individuals, a general orientation toward the wind, the whole group distributed across the available space with an efficiency that any town planner might envy. This distributed, leaderless organization is one of the most impressive things that animal groups do. Each individual follows simple rules. Stay close to your neighbors, don't crowd them, face the same direction. And the result is a coherent group that can respond to the environment together, that feeds efficiently, that takes off together when danger comes. The symmetry that emerges is not imposed from above, but arises from below, from the interaction of many simple rules, many simple beings, each one following the same instructions. Termite mounds are the most architecturally ambitious example of this kind of emergent symmetry. A termite mound in Africa or Australia can stand several meters tall, made of millions of tons of soil and saliva, built by workers who are blind, who have no blueprint, who respond only to what is immediately around them. And the finished mound is a masterpiece of engineering, internally symmetrical, with a complex network of tunnels and chambers, with ventilation shafts that regulate temperature and CO2 to within narrow tolerances, with the royal chamber at the center, the queen resting in the heart of the structure she has never seen. The mound is radially symmetrical when viewed from above. The tunnels radiate outward from the center. The outer walls curve in a roughly circular perimeter, the internal structure repeating in all directions. This symmetry arises without anyone planning it, from the same distributed, rule-following process that gives a murmuration its flow and a flock its spacing. The termites build according to pheromone signals. Where there is more material, there is more signal, and more material is added until the structure completes itself. Nature builds its most elaborate symmetries from very simple starting points. This is perhaps the most important lesson hidden inside all this beauty. That order does not require a plan. That symmetry does not require intention. It arises patiently from the repetition of very simple things. Your breath rising and falling, a wave moving toward the shore, a ring of growth added to a tree. Simple things, repeated, making something larger and more beautiful than any of their individual moments. Let your breath be simple. Let it be just breathing, just the rise and the fall, just the oldest rhythm in your body doing what it has always done. The inside of a geode is one of the great quiet surprises of the mineral world. On the outside, a geode is an unremarkable lump of rock, gray, rounded, giving no indication of what it contains. But cracked open, it reveals a hollow lined with crystals, amethyst, quartz, agate, celestite, calcite, growing inward from the walls, pointed and purple or clear or white, catching the light and breaking it into small rainbows. The crystals inside a geode grow toward the center, each one in competition with its neighbors for the dissolved minerals in the groundwater that percolates through the rock. The result is a kind of radial symmetry, the crystals pointing inward from all directions, meeting in the center of the hollow. If the geode is perfectly spherical and the crystals have grown evenly, the center might be entirely empty, a small void, the most symmetrical space of all, surrounded by the pointed and orderly abundance of the crystals. Every geode began as a bubble of gas trapped in lava, or a hollow space left by an organic structure dissolved in sedimentary rock. For millions of years, mineral-rich water slowly deposited crystals on the inner walls, layer by layer, molecule by molecule, until the hollow was lined with whatever mineral was most available in that particular groundwater. Each geode is a record of the chemistry of its environment, expressed in the symmetry of crystals. To hold a geode, that modest gray exterior, that interior glittering world, is to hold a long and patient secret. The world is full of such secrets. The smooth stone on the outside, the crystal garden within, the quiet night, the dreaming mind, the ordinary day, the extraordinary life that lives inside it. We are grateful you are spending part of this night with us. If these stories have become a regular part of how you find sleep, we would love to see you in the comments, just a word, whenever the morning gives you a moment. Now, gently, let's continue. The symmetry of a seashell collection laid out on a table is a kind of taxonomy of the sea's geometries. Here is a cone shell, its exterior cone with a radial symmetry, its aperture a long, narrow opening edged with small teeth. Here is a cowrie, its oval form smooth and bilateral, its slit-like opening revealing a ringed interior. Here is an auger shell, a long tapered helix, its spiral winding tightly from broad base to narrow point. Here is a scallop, its two valves identical in their fan shape, their matching ribbing, their symmetrical hinge. Every shell is the record of a life, of an animal that built its house around itself as it grew, adding new material to the lip of the shell with each growth pulse. The shape of the shell determined by the speed and the angle and the amount of growth at each part of the lip. A shell with an even shape is a shell that grew evenly. A shell with an irregular bulge or a sudden change in spiral angle is a shell that survived something, a disturbance, a near predation, a lean season. The symmetry of the shell is the autobiography of the animal. We share this with shells more than we might think. The lines on our faces, the asymmetries in our bodies, the particular way we hold ourselves. These too are records of how we have grown, what we have survived, what seasons have been lean and what seasons have been full. We are our own autobiographies, written in flesh rather than calcium carbonate, carried with us rather than left behind on a beach. But a shell left on a beach is a gift. Someone else can pick it up, hold it, feel its weight and its smoothness, put it to their ear and hear what? Not the sea. The sea is not in the shell. What you hear is the ambient sound around you, amplified and filtered by the resonant chamber of the shell into something that sounds like the sea. The shell gives back to you your own world, transformed, made resonant, made oceanic. Hold that image gently, the shell that gives back the sea, the world reflected in the dewdrop, the mountain reflected in the still lake, the snowflake that is unique and yet always sixfold, the tree that is different in every ring and yet always growing outward from its center, the living world, always finding the same forms, always making the same patterns, always returning to the same deep symmetries, generation after generation, with the faithfulness of something that knows, without knowing it knows, that this is the right way. You know it too. Somewhere in you, you know it. The rhythm of your sleep is the rhythm of the tides. The pattern of your cells is the pattern of crystals. The branching of your veins is the branching of rivers and trees and lightning. You are made of the same instructions as the Nautilus and the morning glory and the spider's web. Rest in that knowing. Let it be comfortable. Let it be the ground beneath you, as solid and patient as the oldest stone. Let the rhythm of the turning earth carry you. Let the sound of your own breath be the last sound you hear. In and out, in and out. The oldest and most faithful music, the most symmetrical thing you have ever known, always there, always even, always bringing you back. Good night. You are safe. The world is beautiful, and you belong in it. Sleep well.